Vector-based retrieval systems rely on contextual language models to extend search capabilities, but their reliance on GPUs can be expensive and difficult to manage. To address this, researchers Daniel Campos and ChengXiang Zhai propose leveraging unstructured sparsity in language models for dense retrieval. By doing so, they demonstrate that sparse language models can be used as direct replacements for existing models, achieving up to 4.3x more queries per second with little to no loss in accuracy. The authors provide an overview of related work, including the use of B-encoders, dual encoders, and dense retrievers in information retrieval, which have been shown to be highly accurate and efficient when paired with approximate nearest neighbor algorithms like FAISS. Recent advances in introducing sparsity into small and large language models have also resulted in improved inference efficiency with minimal loss in accuracy. The main contribution of this work is the demonstration of using unstructured sparsity in vector-based retrieval combined with a sparsity-aware inference engine. This approach achieves significant improvements in queries per second with negligible accuracy loss. Experiments on the MSMARCO, natural questions, and TriviaQA passage retrieval datasets showcase the potential of sparse language models as drop-in replacements for existing models. By leveraging unstructured sparsity, practitioners can realize inference speedups without additional effort, making it an attractive solution for those seeking to improve performance in information retrieval tasks. This novel approach has significant implications for enhancing the efficiency of vector-based retrieval systems. Dense retrieval, a technique used in information retrieval, involves creating query and document representations in a shared latent space using a representation model. This is achieved through tied or untied B-encoders, aiming to minimize the distance between positive query document pairs. The loss function for this process is given by equation 1, where x and y represent the query and document vectors, respectively, and denotes the dot product. L equals 1, x, y, x, y. To apply sparse transfer learning to dense retrieval, pre-trained sparse language models are utilized. Specifically, the Aubert 12-layer encoder model is employed, which exhibits 90% unstructured sparsity and 80% block sparsity. This model is used as a drop-in replacement for the uncompressed BERT base. The effectiveness of the Aubert models is evaluated on various retrieval datasets, including MSMARCO v1.1, NQ, and TriviaQA passage retrieval datasets, using the Tevatron library and Hugging Face transformers. The training hyperparameters used are listed in Table 1. The results are evaluated by measuring recall accuracy with retrieval depths of 20, 100, and 200. Computational experiments are performed on 16 GB V100 GPUs, with 1 V100 used for MSMARCO and 4 for each other experiment. The training hyperparameters result in higher learning rates for the sparse language models. The use of sparse transfer learning in dense retrieval has the potential to significantly improve inference throughput, making it an attractive approach for real-world applications. The results of this study provide valuable insights into the effectiveness of this approach and its potential applications in information retrieval. Table 2 presents the retrieval accuracy at 100 and inference throughput for various models, including BERT base with PyTorch and deep sparse, as well as Aubert with different sparsity levels. The results indicate that the use of sparse language models can lead to significant improvements in inference speed without compromising accuracy. Specifically, the Aubert 90% sparse model achieves a 4.28x speedup over the BERT-based PyTorch model, while maintaining a retrieval accuracy comparable to the dense baseline. In the inference benchmarks, the authors evaluate the performance of query encoding using an Intel Xeon Gold 6238R processor with native PyTorch inference and the sparsity-aware inference library Deep Sparse. The results show that simply switching from PyTorch to Deep Sparse can lead to a 1.7x speedup, and that the Aubert 90% sparse model outperforms the Aubert 80% block sparse model in terms of both inference efficiency and retrieval accuracy. Figure 1 plots the retrieval performance of the sparse language models relative to the dense BERT-based baseline, demonstrating that it is possible to improve inference performance by nearly 4.3x with less than 1% loss in accuracy. The detailed results in tables 2, 3, and 4 reveal that the use of sparse language models works well with both tied and untied B encoders, but performance improves when the B encoder is tied. This is attributed to the query and document encoder sharing the less expressive sparse language model. The impact of using sparse language models is more pronounced with smaller recall sets. When the recall set is 20, losses range from 1.3% to 3%. While expanding the recall set to 100 items results in minor improvements to under 2% losses. The authors also explore the introduction of quantization during training using COT and post-training, but find that this causes a near-complete collapse of retrieval accuracy. The findings in this work demonstrate the potential of sparse language models for vector-based retrieval. The use of sparse language models can lead to significant improvements in inference efficiency without compromising accuracy. Future work aims to explore the combination of sparse language models with quantization and structured pruning to further improve performance, as well as investigating the role of sparsity in smaller models and cross-encoders. The authors present a comprehensive compilation of methodologies, algorithms, and mathematical concepts in their research paper. This work aims to provide an in-depth analysis of various techniques used in the field, with a focus on technical accuracy and clarity. The paper begins by introducing key terms and concepts that are essential for understanding the subsequent sections. It explains complex ideas such as algorithmic complexity, data structures, and computational models, ensuring precision and clarity throughout. One of the significant contributions of this research is its detailed explanation of novel algorithms developed to solve specific problems within the domain. These algorithms are thoroughly described, including their purpose, significance, and potential applications. The authors also summarize equations and mathematical concepts efficiently, highlighting their role in the development of these algorithms. In addition to discussing methodologies and algorithms, the authors also delve into the limitations and assumptions associated with each approach. This section is crucial as it allows readers to understand the potential pitfalls and areas for future improvement in the field. The paper also includes figures, tables, and graphs which are condensed without losing essential details. These visual aids serve to illustrate the concepts discussed in the text, providing a clearer understanding of the subject matter. The authors maintain connections to content from previous sections, ensuring continuity and coherence throughout the paper. This helps to create a seamless flow of information, making it easier for readers to follow the argument and appreciate the depth of the research. Finally, the authors identify areas for future work, outlining potential avenues for further investigation and development. This section not only demonstrates the author's commitment to advancing the field but also serves as a valuable resource for researchers looking to build upon the presented findings. Overall, the authors have successfully created a comprehensive guide that serves as a valuable reference for both novice and experienced researchers in the field. The performance of sparse transferred Aubert models is evaluated on 3 passage retrieval datasets: NQ, TriviaQA, and MSMARCO. These models exhibit varying levels of tied sparsity and block sparsity, with results presented in tables 35. On the NQ dataset, Aubert models with 90% tied sparsity and no block sparsity achieve accuracy rates of 78.78% at 20, 85.84% at 100, and 87.70% at 200. In contrast, Aubert models with 80% tied sparsity and block sparsity achieve accuracy rates of 78.48% at 20, 85.62% at 100, and 87.17% at 200. For comparison, BERT-based models with no sparsity achieve accuracy rates of 79.83% at 20, 86.34% at 100, and 88.42% at 200. On the TriviaQA dataset, Aubert models with 90% tied sparsity and no block sparsity achieve accuracy rates of 78.40% at 20, 84.41% at 100, and 86.10% at 200. Aubert models with 80% tied sparsity and block sparsity achieve accuracy rates of 79.31% at 20, 84.81% at 100, and 86.49% at 200. BERT-based models with no sparsity achieve accuracy rates of 79.62% at 20, 85.33% at 100, and 86.72% at 200. Results on the MSAMRCO dataset show that ABERT models with 90% tied sparsity and no block sparsity achieve an F1 score of 32.76589007 and accuracy rates of 61.46% at 20, 70.04% at 100, and 85.37% at 200. ABERT models with 80% tied sparsity and block sparsity achieve an F1 score of 32.51235958 and accuracy rates of 60.69% at 20, 69.63% at 100, and 84.50% at 200. BERT-based models with no sparsity achieve an F1 score of 32.20429117 and accuracy rates of 60.21% at 20, 69.80% at 100, and 85.29% at 200. Inference benchmarks for BERT-base and ABERT models are presented in Table 68. These results indicate that ABERT models can achieve competitive performance to BERT-base models on passage retrieval datasets, while also demonstrating improved inference efficiency. Specifically, ABERT models with 90% tied sparsity and no block sparsity achieve an average items sec of 202.67, full time of 17.83, and mean time of 4.34 times 10 to the 3 using deep sparse, outperforming BERT-based models with no sparsity. Inference benchmark results for ABERT 80% block using deep sparse are presented, showcasing the model's performance across various metrics. The model achieves an average of 141.78 run items per second, with a standard deviation of 4.63, and a mean time of 6.42 times 10 to the 3 seconds, with a standard deviation of 2.52 times 10 to the 4. Percentile analysis provides insight into the model's performance under different loads. The 95th percentile is 6.44 times 10 to the 3 seconds, indicating the model's performance under high load conditions, while the 50th percentile is 6.21 times 10 to the 3 seconds, and the 5th percentile is 6.16 times 10 to the 3 seconds. The 99th percentile is 9.42 times 10 to the 3 seconds. Confidence intervals are reported, with a lower bound of 137.72 run items per second and an upper bound of 145.84 run items per second for the average run items per second, and a lower bound of 6.20 times 10 to the 3 seconds and an upper bound of 6.64 times 10 to the 3 seconds for the mean time. The use of deep sparse, a deep learning inference engine, enables a comprehensive evaluation of the model's performance in a real-world setting, taking into account hardware and software configurations. The results provide a detailed understanding of the model's performance and can inform decisions about model deployment and optimization. The statistical framework provided by confidence intervals and standard deviations enables the identification of areas for improvement.